Okay, this video is about um, mainly about the Graham-Schmidt theorem or method for finding orthogonal bases, um, factoring, and the change of coordinates. So those are the main three things we want to go over: Graham-Schmidt, factoring, and um, change of coordinates. We change coordinates if we change bases. So a basis gives you coordinates. Rather, when you have a basis, you can build a. Let me show you what we mean here, real quick. So if we have a basis for r squared, okay, the standard basis is just 1, 0, which is this vector, and then 0, 1. So if you want to locate a point, say 2, 3, about there, what you do is go 2 units this way, and then 3 units this way. So the coordinates are 2, 3, which means do 2 of those, and then do 3 of those, and you get to that point, to that location. But let's make things a little simpler. Let's say instead of using, we can label this as E1 and E2. We can replace those two, which form a basis for r squared. And a basis means that all the linear combinations of those two vectors are going to give us all the space. So you can have a basis with E1 and E2, or you can have a basis with other two vectors. Say, let's keep E2, um, but we're going to use another vector, say this one. Yeah. So this is another vector, which we're going to label with another letter, say little a. So a, E2. Can we get to this point using this vector and that vector, not this vector any longer? And the answer is yes. The thing is, you have to go, okay, so assume this goes 1 unit and 1 unit down this vector a. So since we want to end up lined up at 2 on the right, you want to use 2 of those vectors, 1, 2, which puts you down underneath 2 units. And then we will need 5 of those to get up here. So 2, 3, using coordinates E1, E2, or using E1 and E2 as our basis is the same thing as, so this is with E1, E2. That is the same thing as 2A and 5 of the other. So that would be A, E2. What I'm trying to tell you is coordinates are a relative thing. Coordinates rely on what the basis is being used. So if the basis is, it's kind of like the units. What comes to mind is the units. Is pi over 4 the same thing as 45 degrees? And the answer is yes. It depends what units we're using. If we are using a radians, then pi over 4 makes sense. If we're using degrees and we put down 45, rather pi over 4, then they're not consistent. So whatever we write down for an angle has to do with the units we're using, whether it's radians or degrees. Same thing with measurements. If you're using meters versus feet and yards and inches, well, when you put down 2 as a distance, we have to clarify to what? 2 feet, 2 meters, 2 yards. What are we talking about? 2 inches? So 2 as a distance doesn't make sense. Likewise, 2, 3 without a basis doesn't make sense. what happens is that since we were really, really young, we've been told, oh, 2 is the horizontal and 3 is the vertical. So they are telling us the bases are E1 and E2. From the moment we started doing coordinate access, I don't know, in 7th grade, I don't know, in elementary school or middle school, they have been drilling us. Hey, X is the horizontal, Y is the vertical. X is the horizontal, Y is the vertical. Horizontal, vertical, horizontal, vertical. So when they tell us that hundreds of times, and it's okay, I'm not going against it. Um, then we are stuck, but the danger is that we are stuck with thinking, oh, that's always horizontal and that's always vertical. Wait a minute. Yes, if we use this standard um, writing, that this is the basis uh, is horizontal first and vertical second. But in some strange way, and you may be thinking, wait, but that's not standard. Yeah, but that's the whole point. We got to open up our mind to other kinds of bases. So we can have another basis that starts with this, and we may be thinking, wait a minute, but that's totally not standard. And the answer, or to my reply to that is, so what is the problem with that? There's no problem not having a standard. As long as we are aware of what we are doing, we can use this and that as a basis. Now, that would contradict a decade or so for many of students of the drill of horizontal and vertical, because then this would mean diagonal down of 45 degrees, which is kind of awkward. I agree. So do 2 of those, and then we gotta, because that brings us down here, that now we gotta climb up, down here, we gotta climb up to this point. So we have to compensate because we initially went down. We have to compensate by going up 5 units. So is 2 5s the coordinate to this? And the answer is yes, if we are using this basis, this vector, and that vector. And you can change basis. So let me go back. Let's label this as example 1. Okay, so there's the standard E1, E2, and if we do 1, 2 of E1s, and then 3, 1, 2, 3, we're going to be here at what is classically called 2, 3. Okay. All right. But if we, so that is the basis, those are the coordinates of this point using E1, E2, and we're assuming this guy is E1 and this one is E2. But now I'm introducing another coordinate, this one, another coordinate system. So if this one is A and using this one as E2, how do I get to this point without using this and only using A and E2? Okay, so the way we go about it is go 1, 2, so that we are lined up here, and then we can go up straight up 1, 2, 3, 4, 5. So the coordinates 2, 3 is the same thing as the coordinates 2, 5 using A, E2 as the basis. So we can use a different basis to generate every point. The coordinates are going to be different. Let's say I want to use this vector. So 1 unit, 1 unit, 1 unit down. So let's call this vector B. And I'm just arbitrarily, coming up with vectors. Arbitrary and not, because I want to make sure I'm able to get to this point reasonably easily. Okay. Can I get to this point using A and B without using E1 nor E2 at all? And the answer is absolutely yes. Those two are linearly independent, and consequently, we can generate all of R squared using those 2 vectors. How do I get to this point using those 2 vectors? There's another way to go about it. Let's see. We can, I have to draw some auxiliary lines here to see. Okay, so see, this vector goes to the left and down, but I want to go sort of up um, and to the right. So that means we're going to use the negative of b. So this would be a negative b. Um, my units are sort of messed up. This would be another negative b. Yep. And then we can start here using the b direction, but then we have to go on the opposite of a direction, but about half the way. So if we do negative half a, so that is the same thing as negative half a, comma, and then 1, 2.5 of b, so that is 5 halves of b, whoops, 5 halves, oh, that's not working anymore. I just got a new eraser. Oh yeah, I guess this is the eraser. Yeah, it does work. So 2, there we go. So those are the coordinates of the very same point. So the point is this one, using a and b, a, b as the basis. So if you go half distance negative, because it's a goes in this direction. So if I right and down, if I want to go left and up, we got to do the negative of a. Well, negative in this case, negative of a. So go negative half the way, because this guy goes all the way here. So we want to go like to the center of this square with -1 and -1. So we want to go about half the way. And then we go half, 1, 2 full units, and that will take us to the same point. And you may be thinking, boy, that is really, really, really cumbersome. Why are we complicating our lives? I mean, 2, 3 is 2, 3. What? That's the end of it. Why are we changing the basis so that that it looks really confusing? Here's the deal. Changing the basis is somewhat similar to changing languages. And that's kind of like saying, well, if you grow up in the United States, you're very familiar with English. So if they speak to you in French, you're gonna say, well, I don't get, why are you talking to me in French and or in or in Russian or on Chinese, or that is gonna sound confusing. We were not gonna understand anything unless we have some kind of training on other languages. And that's kind of what's going on here. We are very familiar since we were children, literally, with 2, 3, the coordinates. That works beautifully. But we have to be aware that there are other systems, other bases that can locate elements just as good as E1 and E2, which is the basis we grew up with. Just like English is the language, perhaps, that we grew up with. So what are other systems? And the thing is that there's millions of systems of bases that we can come up with, just like there are many, many languages, and then there's dialects and so forth. So that's kind of what's going on here. This point under our standard, now, so the word standard starts losing some value. Standard to us, yes. And I have to admit that is pretty universal. It's standard, throughout. Yes, but that doesn't mean there is other systems, and we can make up our own system, A, E2, that under which the coordinates are not going to be the same. They're going to be 2, 5. A and B, the coordinates are going to be -1/2, comma, -5/2. So this point here has coordinates. I'm going to cover this with my thumb. Those are the coordinates of this point if we use those two vectors. Isn't that wild? Yeah, so those are the coordinates of this point. Never mind what it is in standard, even though if I uncover my thumb, if I put move my thumb, we can see the coordinates, but let's cover it again. Whatever it is, this point as a location, as a spot, as a place, has coordinates, those coordinates using A and B. If we use A and E2, those are the coordinates. If we use standard coordinates, E1, E2, those are the coordinates. So the concept of coordinates is relative to the basis. Please be very, very aware of that, because that's kind of moving the earth under us a little bit. It's like, I thought I was on solid ground when I was always talking 2, 3. I mean, they always told us since we were children what 2, 3 meant on the coordinate system. What they didn't tell us is that that is based on E1 and E2. But if you have a different system, a different coordinate system, then the coordinates are going to be different. The numbers we use to locate the same point are going to be different. And again, this brings me back. I just think that's a good analogy. I'm not saying the book is the best in the world. It is. I mean, I read it, so but it's a good analogy. Ender's Game. You know, when they all when Ender always talks about, not always, but frequently talks about you know, what down means, up, and gravity and all that. That's kind of similar to this. You know, on Earth we're thinking, okay, down is where my feet is. But that is relative. That is completely 100% relative of the system in which we are. I mean, if you go to the other side of the world, we are upside down. Or the people on the other side of the world, they are upside down relative to us. So what up is and left and right is relative to a system that we have. And that's what this is about. If we stick with E1, E2, this makes perfect sense. But if we start moving the bases, then the system has different coordinates. The point never changed. Mind that. The point is, the location is the same. What changes are the coordinates that we're using to get to that point, because, well, now we have different coordinates. Now, some coordinates, I'm going to do a new picture. I'm going to try to stick with the same point, 1, 2, 1, 2, 3. Okay, so I'm going to come up with new ones. So let's say there is a vector here. I'm going to call it C. And I'm trying to think. So that is 2, yeah, and D. Yeah, yeah. So can we get to this point using C and D? And the answer is yes. This point is 2 units to the right, 1 up, this C, and this is 1 to the right and 2 up. So they are symmetric relative to those 2 lines. In other words, by symmetric, I mean this. They make a nice V and the angles are the same. Okay, that means using the parallelogram rule, if we add those 2 together, we're going to end up with a line in between, or we're going to end up with a point that is right in between. So if we add D to C, now D goes 1 over and 2 up, so 1 over, that's going to put us at 1, 2, 3, and then up 2 units. So we're going to overshoot. We're going to be beyond this point. So if we put, again, C plus D, we're going to be past this point. This point is 2, 3 in regular standard coordinates. I'm just making a new system because otherwise this one will get too busy. Okay, so I'm trying to figure out the coordinates relative to C and D for this point. Can we find them? Yes. Oh, my bad. This is 2, 3. For a moment, I thought this was 45 degrees. Yeah, this point is not in the middle, in the diagonal. Let me draw a better picture. Boy, I really have to draw the coordinates here. Yeah, so there's the point in question. This is one vector, and this is another vector. The question is, can I get here using C and D? This picture is a little better for me because I can clearly see the actual unit. So this point is 0, 1, 2, 0, 1, 2, 3. There we go. Now we can go this way. So we can add D, but now I got to come back to this. So I have to use negative C somehow. Oh, or perhaps, see, it gets complicated to get to this point using those two. Can we do it? Actually, it's not too big of a deal. Let me just show you very quickly. So how we do this, because that is important. So C is the same as 2, 1, 2, 1. That's C. D is 1, 2. Can we get to 2, 3 by a linear combination x plus y of those two? Sometimes I'm going to be using C1 and C2 instead. Can we get to that point, and how? Well, we can do this algebraically. So this has 2x plus 1y equals 2, and then 1x plus 2y equals 3. Okay, we can multiply the second equation by 2, so 2x plus 4y equals 6. And then we can subtract this equation minus that equation. Technically speaking, I should be using matrices, but the algebra got the best of me. So 2x minus 2x is no x, y minus 4a is 8y rather, y minus 4y is negative 3y. And then 2 minus 6 is negative 4. So that means that y equals 4/3. So if y equals 4/3, then, well, here it's going to be easier. So putting this back into here, again, matrices makes this a little neater than that. That's why we use matrices oftentimes. So x plus 8/3, because y is 4/3 multiplied by 2. So now we got 8/3 equals, anticipating we're going to subtract 8/3 from both sides of this equation. I'm going to convert the 3 into thirds. So we have 9/3. And so x is really 1/3 and 4/3. So x equals 1/3, y equals, I'm going to make it as a mixed number. And we usually don't, but I want to show you why it was difficult to get to this just by drawing the picture. So that means we have to go on the C. Remember, x is then the scalar we multiply this vector by. So 1/3. So we have to move this, we have to shrink it to 1/3 of it. So it's going to be about there, the 1/3 of C. Now a whole D is going to take us, because D is 2 units tall, that's not going to make from here to here. If we just add D, that's not going to reach this point up here, which is the one we want to reach. Okay, this is longer than D, longer. How much? Well, it has to be 1 1/3, kind of like 133% of what D is to get to this point. So can we get to this point using C and D? And the answer is absolutely yes in this case. The coordinates, okay, so remember how we have the coordinates here? So the coordinates are 1/3, comma, 4/3 if we use CD. I know it's a little confusing, but please, the main, or look, the main thing that is going on here is that we are changing our basis. So the coordinates we use are relative to the basis. It's like saying, it's like the words we picked, we speak, we use are relative to the language we are speaking. You know, how are you? Comment allez-vous? In French, and there are other languages. So what are we going to say to ask how you're doing depends on the language. So what coordinates are we going to use? It depends on the basis. So the bases are the two vectors in R2 that generate all of the space. And we may change that base if we wish, if we choose to. Yeah. Now, having said that, there are bases that are better than others. So having said that, that we can change the bases pretty much arbitrarily. There are some bases that are better than others. That is an interesting concept. There are bases, yeah, that are better than others. Now, I'm going to put better in quotation marks because even that is relative. That is relative. Uh, better is is relative. So we have to define what we mean by better. Better under what criteria? We cannot just say, oh, this is better than this other thing. Under what criteria? What's the criteria we're using? Better is very relative. Um, yeah, yeah. Using better without establishing the criteria we're using is really meaningless. Anybody can say this is better than this other thing, but we have to establish for what purposes. How are you measuring better? Um, and here I'm gonna talk about languages just very, very briefly. For instance, how is one language better than the other? Well, some of them are more technical. So writing technical, scientific things with one language makes it way, way better. Some other languages are more romantic. So writing poetry, perhaps, um, is a little better. And then again, and even with that, somebody could say, wait a minute, maybe that's the way we learned how languages work. So I agree. Even that could be subject to being subjective. Yeah, yeah. The way we perceive languages could even be subjective. So what the important thing is, when we say that something is better, we have to tell the criteria. What do we mean by better when we are talking about different bases? And here's where some definitions are important. Let's talk about the length of a vector first, and then the orthogonal vectors. That under this criteria is that we're going to establish that one base is better than the other. Length of a vector and orthogonal vectors. Okay, so length of a vector. So the length of a vector will be um, dependent on the will be defined depending on the length of the vector. What I mean by that, the dimension of the vector. So if you have a two-dimensional vector, A, B, okay, the length of it, some books use this, some books use double bar. So whenever you see vertical bars around a vector, a one-dimensional vector, such as what I mean by that, it's not a matrix that is like two columns, just one column. When you see that, or the double bar, that means we're talking about length. And for a two-dimensional vector, we mean the square root of a squared plus b squared. So that is the length. The length of a three-dimensional vector, a, b, c, will be the square root of a squared plus b squared plus c squared. And we cannot really simplify that. You just have to figure that out, adding the numbers. If you have a one-dimensional vector, I wanted to squeeze it here. So its length is the square root of a squared. This one we can simplify as the absolute value of a. Yeah. So perhaps that's why we use the same notation for this, like sort of the absolute value of the vector AB is this, but we cannot simplify it. We cannot say, please do not say, not at all, that this is somehow A plus B. That's not true. I'm even going to cross it off. Now, this is it. The only time we have that the length of a vector is equal to the absolute value of a number is when we have a one-dimensional vector, which is very, very simple. But in this case, as soon as we get two, which is going to be most of the cases, 2 or 3 or 4, we're not going to be able to put this into absolute value uh, terms. And I think we can easily extrapolate to finding the length of a vector that has 4 coordinates. A, B, C, D will be square root of a squared plus b squared plus c squared plus d squared. Okay, so that is the length of a vector. It is very, very desirable. We desire to have bases whose length is 1. Also known as, so if we have a vector of length 1, then we label it as unit vector. So for instance, and that's why the standard, that's one of the reasons why the standard basis E1, E2 is desirable, because the length of this vector is a nice 1 and 1. The length of this vector is not 1, it is the square root of 2, if because you go 1 over and 1 down. So you have a triangle, a right triangle, and by Pythagoras, 1 plus 1 is 2, and then you take the square root. So the length of this vector is the square root of 2. And so is this one. So that is not as desirable as this one. And the reason is because we don't want to modify, when we give coordinates, we want to have an idea of the length, the distance we're covering using those coordinates. So when we say, where's AB? Yeah, when we say a half, so we mean a half of this, but that is not really a half of a unit. It is a half of this length, but this length is not a 1. So that is kind of changing the focus, the idea of what 1/2. We want 1/2 to represent 1/2 of a unit. I guess that's what it boils down to. In this case, we are talking about half of this vector whose length is not 1 unit, and that really skews the length. So it is desirable that vectors have a length of 1. Just like a ruler. You want a ruler to be, when you buy a ruler, and you use it to measure things, how long is this ruler? A foot. Yeah. So it is a foot ruler. Would you buy a ruler that is 11 inches? I mean, you could, it will work, but it's kind of awkward to use a ruler that is, or 7 inches. Why not just a whole foot? Maybe half a foot is good, 6 inches is good, But a weird measurement to buy a ruler, if I want to measure, even if I have just this basic ruler to measure, the desk, I just place it and then I, walk it over, I flip it over, and then I just measure it that way, and that tells me the feet that the desk is. But if this was, say, 7 inches, which is like a weird measurement, then when I start measuring it, I have to multiply it by 7, and I get the inches, and then I have to divide by 12. See all the things that I have to do just by when you buy a ruler. We want the ruler to have a unit, a standard unit, which is, in our case, the feet or the foot. So likewise, we want our vectors, our base vectors, to be 1 unit long. We don't want them to be 1 1/4, or as in this case, that would be square root of 2. That's the length of this vector. The length of this vector is square root of 5, because we got 2 squared, 1 squared, add those together, 4 plus 1 is 5, and then we got to take the square root. So this length is square root of 5, which makes it really, really odd. So when we say that the coordinates are 1/2, rather 1/3 and 4/3, that doesn't tell me how far it is, how far we are, because uh, this is 1/3 of the square root of 5. So that's really awkward to, again, it is desirable that if we're locating points using a basis, we want our basis to be 1 unit long, unit vectors. Now, can we fix A, B so we have unit vectors? And the answer is yes. Okay. So A, as a sub-example of this is not an example, this is explaining what length is. So, but as a sub-example, okay, A has coordinates 1, -1. And I'm still speaking about this A that I introduced in example 1. So there is A, 1, -1, there is A. What is its length? Let's use the formula. So A equals the square root of 1 squared plus -1 squared, which is square root of 1 plus 1, which is the square root of 2. In particular, this is not 1. We can always shrink or stretch a vector so it becomes of length 1. If we multiply by the reciprocal, we create a new vector, and that would be 1 over the square root of 2, 1 comma -1. Typically, we write it this way, we leave it alone, because introducing the 1 over the square root of 2 into the vector can cause a problem. But it doesn't cause a problem, it's just awkward to work with, cumbersome to work with. So -1 over the square root of 2, there we go. That's going to work way better than, excuse me, this is going to work way better than this vector. Now, some of you may say, wait a minute, the whole numbers were actually nicer. I could understand the whole numbers. These are really weird. Yes, but this vector is more desirable. See, that's what I mean. Whenever we say better, we have to establish a criteria. Better. Yeah, we cannot just, anybody who says, I'm better than you, on what? According to what criteria? It's totally relative. Anybody who says that something is better than something else, they have to, it's not a easy process. Yeah, yeah. To say that and to prove that, and you have to establish the criteria. Anyway, the reason why I'm bringing that up is because, look, I personally, visually, I rather use whole numbers, no fractions. Fractions bring a complication. Square roots that are not simplified or simplifiable is even more complicated in addition to the fractions. So from a visual point of view, this is more complicated to me than that. I'm covering to compare the two. Yeah, this is more complicated. However, from the point of view of distances, this is way more desirable, because when we say 3 of these vectors, then we know we're going to go 3 units. And that in physics and other places like that is desirable. You don't want to change the units. Again, I'm bringing back the ruler. The rulers you buy typically are 1 foot long. It will be weird to buy a 7-inch ruler. I'm sure there are if you look hard enough. In fact, somebody could say, hey, that's a business opportunity. Yeah, just sell rulers of different lengths. So, but that is awkward. Typically, you don't buy those. Some of the compact rulers I've seen are either 6 inches or 3 inches, even the small ones, because they don't want to have an odd number as for the ruler. It makes it kind of weird. Anyway, so this is better. It's not as appealing to the eye because we prefer whole numbers, but it is nonetheless better under our criteria of having a length of 1. So we can we can label this as A prime, nothing to do with derivatives. This is just a way of not calling A, we're going to call it something else. And then likewise, B, 1 over absolute, see, I said absolute value, but technically speaking, it is the magnitude of the vector, is 1 over the square root of 2. And remember, our B is to the left and down. So -1, -1. And that is 1 over the square root of 2, comma, negative 1 over the square root of 2. That's more appealing. Now, I'm not going to right now figure out the coordinates corresponding to those two. Maybe that is something we can do later, but those are not, yeah, those are not. So the coordinates of the point in question, this point up here, where is it? That point under this basis. So now we can have another base. If we label this as B prime, we can have the bases A prime and B prime. And that means we will have a different coordinate for A prime and B prime. It would be a good idea to do that. So what are the coordinates under A prime, B prime? I'm going to write down the problem. So sorry to be silent, but I'm writing the problem. There we go. Okay. So finding those coordinates under A prime and B prime is a good problem to do. Okay, what else is desirable? Orthogonal vectors. Okay. These vectors, C and D from earlier, remember 1, 2, so there is C, and then 1, that's 1, 2, and that was D from earlier in the video. Okay, they have one problem. The length is not 1. Fine. Let's bypass that. Okay, let's look beyond that. So the length is not 1. That's one problem. Those two vectors as a basis have a second problem. They're not best. Remember, we are trying to come up with, yeah, there are bases that are better than others. With a better base, under what criteria? Well, one problem with this is that they're not at a 90-degree angle of each other. We want them to be at a 90-degree angle. Right now, I don't know the angle. We don't really want to know, but what we do know is that they are not 90-degree angle. It is desirable to have them at a 90-degree angle. So we want, and this as a desire, we desire, yeah, for the bases elements, or vectors is better, vectors, to be orthogonal. So orthogonal means perpendicular at a 90-degree angle. Now, but let's establish more clearly what orthogonal means. Let's reintroduce the dot product. This vector is 2, 1, and that vector is 1, 2. Yep. The dot product is this times that, 2 times 1, plus this coordinate times that coordinate, 1 times 2. Multiply and add, so we end up with 2 plus 2, 4. Okay. Two vectors are orthogonal if their dot product is 0. That's the definition. Two vectors are orthogonal. Also perpendicular, same thing. Perpendicular if their dot product is 0. So those are not perpendicular. In physics, and actually, yeah, we want to preserve that, especially in physics. In physics, it is very important whether forces are parallel, if one is pushing the other, or perpendicular. That's very important, because then figuring out the angle is easy in between. If we have those two first considerations, perpendicular and parallel, then finding the angle in between becomes relatively easy. But those two angles are not perpendicular nor parallel. Well, if they were parallel, they would not generate all of R2. But so they're not perpendicular, and that causes our angles to be weird. So again, that is a more difficult case to make, but it's like the ruler. If you have a ruler that is a foot long, then it's easy to measure things. You just flip over the ruler, you walk the ruler over, as you know, across a room, for instance, if you want to measure a room. If you don't have a tape, a long tape to measure something relatively long. Um, so that's kind of the same thing. If we have 90 degrees, then we know we are making corners, 90-degree corners. So when we say the coordinates of this point are 2, 3, okay, we know we go in one direction, whether it would be left or right, one direction, and then you turn 90 degrees, so you make a corner, like a street corner, and then you go on here. And you go in the other direction, 90 degrees, and then you walk, and that gives us a clear understanding of where we are. Yeah. So that is desirable. So there are two things we want. We want bases to be a unit length of one, which is easy to fix, and we want bases to be at a 90-degree angle. That is harder to do because that means we have to change this vector into a vector. So if this is the first vector, C, we're going to keep C as is, but this vector has to go away because this vector is not, it doesn't have a desirable quality, which is, well, two desirable qualities. The length is the wrong length. That's easy to fix. The thing that is harder to do is to make it into a 90-degree angle. So this is the way we do it. I'm going to explain very quickly what we do. So there is C. We're going to keep C, and we go in order. Whatever vectors are given to us first, that's the one we keep. And then the other one, the second one, we modify. And if there's a third one, then we modify. And all the consequent ones we modify. So there is C, and there is D. Yeah. So what we're going to go through a process which is called the Schmidt, the Gram-Schmidt process, in which we're going to modify a basis. So we're going to keep the first one. The second one is going to be changed. So this is the way we do it. We find the projection of this guy onto C, which is going to be this vector. All right, so the projection has the quality that is already, well, this line rather is 90 degrees relative to C. Okay, so what we do is, and this is D, this is, let's say this is P, and C is all the way out to here. So what we do is, this is P, this vector. What we do is D minus P is this vector. That's D minus P as a vector. And we want D minus P. Oh, we replace, let me think for a moment. Yeah, we replace D with D minus P. Yeah, because then this vector has the quality of being made up by this vector. It's using D, but we are anchoring it down to here. And now we can move it back to here. So draw it again here, and it is the same vector, D minus P. This is the new vector. So this vector with this vector are going to be perfectly 90 degrees. So we're going to replace this. So if we start with C and D as a basis, we're going to replace it with another basis, which will have C. And instead of D, we're going to replace it with D minus P. Yeah, simple as that. It looks, I thought it was going to be more complicated, but no, that's it. D minus P, and that's it. Well, there's one more thing. We fix the angle. Now we have a basis that is 90 degrees. Fixing the length is easy. Just so after that, we're going to do 1 over magnitude of C times C, and then we're going to do 1 over magnitude of D minus P times P, no, times D minus P rather, D minus P. And then we'll have a beautiful, beautiful in quotation marks, a beautiful basis. Again, beautiful is in the eye of the beholder. Of course, what do we mean by beautiful? We have to have two qualities. We have to want to have orthogonal bases, and we want the length to be 1. Now, once we see those vectors, they may not look beautiful to us at all. Kind of like those two, I don't think they're particularly beautiful in the sense that, man, they are, they have square root. To me, that's more beautiful because I like whole numbers or integers. So those two without the square root is much nicer. But those two have a quality that is desirable. They are orthogonal. If you multiply them with a dot product, you're going to end up with a negative and a positive. Add them together, you get 0. So those have a quality that is desirable, even though to the eye, they may not look as nice. Yeah. So I kind of walked through a little bit what we're going to do. All right. Let's start with an example 2. Okay, I explained the big picture of what we are doing, but we still have to go through the actual Gram-Schmidt process. So I have a matrix here, 1, 2, 1, 5. Okay, so 1, 2, 1, 5. There's our matrix, 1, 2, 1, 5. And pretend those columns are the basis for R squared. So those columns are a basis of a space. Okay, so think of the columns as a basis of R squared. So they generate 1, 2, 1, 5. They generate the R squared. They are a little bit like our C and a D. They are at a weird angle, but they can generate any point. You can find the coordinates of that point using dot basis, definitely. You may have to do a system of equations as the way we did it here, but then eventually we get to our coordinates correctly. Now, are those two orthogonal and unit? And for sure not. If you go 1 to the right and 2 up, the length of that vector is not 1. It's square root of 5. And 1, 5 makes it even worse. The length of this column vector is the square root of 26 because we add 1 plus 25 when we square. Remember the formulas for the length of a vector. There they are. The length of this vector is a squared plus b squared, square root of that. So no, they're not unit. Now, fixing the unit, the fact that they're not unit vectors is easy. So I'm not going to worry about that until later. Are those two vectors orthogonal? No, they're not, because if we multiply across 1 times 1, you get 1. 2 times 5 is 10. So the dot product, so let me establish that first. 1, 2, dot product with 1, 5 is 1 times 1 plus 2 times 5. And that's going to be 1 plus 10, which is 11. Is that a, what should we call it? Oh, that's not 0. So those two vectors are not orthogonal. So as a basis, this is not a best basis. We want a really, really good basis. And a good basis is, but based on this one though, using this matrix. So we have to change this guy. We don't want this guy. We want to keep this one, but we're going to change this one so it becomes perpendicular to that one. But at the same time, we want this one to be on the same plane as those two. So the way we go about it is by finding the projection of this point onto the space generated by this one. So the projection of this onto this space. And there is a formula that we're going to use. So the projection of 1, 5 onto 1, 2 is the vector. Okay, we have a fraction, and then we're going to multiply with the vector 1, 2. On the bottom of the fraction, we have the dot product of 1, 2 with 1, 2. Oops, I put a fraction, but there's no fraction. It is supposed to be a vector. Yeah, 1, 2. And then the dot product of 1, 2, and 1, 5. 1, 2, dotted dot product 1, 5. I know this is a little confusing. Please keep it straight. So this dot product is going to give us a real number, and this dot product is going to give us another real number. So that is going to be 11. We did that earlier. And that's going to be 5. 1 times 1 is 1. 2 times 2 is 4. 1 plus 4 is 5. Times the vector 1, 2, which is the vector 11 over 5, 22 over 5. Okay, so we got this vector. Okay, let me draw a picture. 1, 2 is somewhere in here. I don't know. I'm not going to make this precise as far as the coordinate axis. So this is 1, 2. 1, 5 is somewhere else. By the way, 11 over 5 is bigger than 1. This is 2.2 actually. So this is 2.2 as a number. So 1, 5 is far away. 1, 5 relative to this. But we want a projection. So we want to know the point here, P, on this line where this angle is 90 degrees. Okay. So this is P, and that's why this is farther. This is 2.2. 11 fifths is 2.2. So that accounts for 1, 2.2. Okay. So this is 1, 2, and this is 1, 5. We're going to replace 1, 5 with this vector. So now we got to figure out this vector. Now P is not the vector we're going to replace 1, 5 with. Mind, this vector will be a bad vector, really bad vector, as a basis using this one along with it, 1, 2. Because 1, 2 and this vector are in the same direction. So they're not going to generate all the points in R squared. So be careful. Don't stay with this guy. What we're going to do next is subtract 1, 5 minus this, and that's going to give us this vector, which will be perpendicular. Okay, so we're going to continue with example 2. Continue example 2. We're going to take 1, 5, rather, yeah, 1, 5. And we're going to subtract 11, 5, 22 over 5. 11 over 5, 22 over 5. Okay, so that means we have to change this into fifths. So that is 5 fifths minus 11 fifths. So I'm doing 1 minus that. That's 5 fifths minus that. And then 5 is 25 fifths minus 22 fifths. And of course, the reason why this is 25 fifths is because we are changing 5 into fifths. So this is one vector. And 5 minus 11 is negative 6 fifths. And 25 minus 22, 3 fifths. Okay. So this matrix will be changed into a new matrix. The new matrix is 1, 2, negative 6 over 5, positive 3 over 5. Now, this matrix, the columns form a basis for the same space as the space of this. Let's label this as A. Okay, so is this A? No, it's not. Let's label that as B. What we know is that the column space of A is the same as the column space of B. Yeah, they generate, the columns generate the same space because this is a linear combination of those two. Yep. And so, and they generate the same space. Another notation that we use is that the column space of A is equal to the column space of B. That's what we just established. The column spaces are the same. Okay, so this forms a basis. What's better about this basis? Why is this matrix or this basis, those columns, better than the columns in A? Well, let's perform the dot product. I was gonna squeeze it in here, but I better use a new piece of paper. So let's multiply the columns. 1, 2, dot product with negative 6 over 5 and positive 3 over 5 is, well, multiply 1 times negative 6 over 5 plus 2 times 3 over 5, and that is going to be negative 6 over 5 plus 6 over 5, which is 0. Yes, that means that those two vectors are 90 degrees from each other, for sure, for certain, absolutely, completely. No question about that. Those columns are better than the columns in A because they're orthogonal. Remember, we want the best basis. A best basis has to be a basis where all the vectors are orthogonal with each other. If we have 3 vectors, then all the ways we can pair 2 of the 3 have to be 90 degrees with respect to each other. That is desirable. So this one is better. But there's one other criteria we have to fulfill. The length of the vectors, the length of the columns has to be 1. The length of this is not 1, but we know it is 5. So fixing this column is easy. And I always leave fixing the column last because coming up with perpendicular vectors, with orthogonal vectors, when you start with roots is really, really messy. So I always do the roots last. Okay, we know that the length of this vector is 5. So the way to fix the first column will be to divide by 5, rather by the square root of 5. I think I said that the length is 5, but I meant to say the length of this column is square root of 5. So we divide 1 by the square root of 5, and then 2 by the square root of 5. Okay, that column is fixed. In order to fix this column, we have to find the length of that column first. So on hold, because we need to find the length of negative 6 over 5, 3 over 5. And actually, we're going to do that length in 2 different ways. So we know this is the square root of this squared. Now, when we square, the negative goes away. So this is 36 over 25 plus 9 over 25. And that is equal to the square root of 45 over 25. Don't simplify that because this splits into the square root of 45 over the square root of 25. And that is 5 in the denominator. And then we simplify the root, which is 3 square root of 5. And you can probably simplify that even more. Depends on whether you want a rational denominator or irrational denominator. Yeah, let's simplify it. So square root of 5 over 5 simplifies down to 3 over the square root of 5. Because 5 is the same thing as square root of 5 times the square root of 5. And so 1 square root of 5 cancels off, but we still are left with a square root of 5 in the denominator. Okay, so we have to divide each element of matrix B by 3 over the square root of 5, which is the length of that column. Okay, so I'm going to do that. I really want to finish on this page, so I'm going to carve some space here. Okay, and I'm going to multiply negative 6 over 5, negative 6 over 5, and we're going to divide by 3 over the square root of 5, which means multiply by the reciprocal. So multiply by the reciprocal, square root of 5 over 3. Interesting. So the 6 and the 3 simplify to negative 2. And again, those two simplify, and we keep the square root of 5 in the denominator. So negative 2 over root 5. Oh, I'm going to show you a trick to get to that answer faster. And then 3 over 5 multiplied by the reciprocal of this, because we're going to divide by that length, square root of 5 over 3. The 3 simplified, the square root of 5 simplified, so we end up with, with 1 over root 5. Okay, this is not the same matrix as B, mind. It's not the same matrix, and just as much as B is not the same matrix as A, but it generates the same space as the columns. The columns of this matrix generate the same space as the columns of column B, which also generate the same space as the columns of A. So we label this guy as C. And this is the best matrix as far as generating the same columns as the matrix, but rather generate the same space as the space generated by the columns of A. That's the best matrix. And you're going to think, whoa, A looks pretty nice to us, 1, 1, 2, 5. This looks really awkward and weird. Yes, I have to admit that. To the eye, this is more pleasing, at least to me, than this. But this does not fulfill the criteria. Where's the criteria? The columns have to be orthogonal to each other. They're not. The lengths have to be 1. They're not. So it's perhaps pleasing to the eye, but it's not a, it doesn't fulfill the criteria. Yeah. Yeah, and boy, I can go on a tangent with that. Like you can pick, I don't know, a car that is pleasing to the eye, but maybe the car is not reliable, and maybe you know uses too much gas, and it is not safe. There are some criteria under which another car that may not be, when you are buying a car, um, may not be as pleasing to the eye. It may not look as nice, but under other criteria, it is what we want. That, and I can go on a tangent with that. You can apply that to anything, or if you're looking for a partner, uh, you know, I don't know. I don't want to go there. Never mind. One way to make this a little more pleasant is factor out the square root of 5. Everybody has a square root of 5, so we can factor that out, and then our matrix looks a little better. 1, -2, 2, 1, and it is the same matrix, and that looks a little better. Just keep in mind, if you're going to pick the column, you have to multiply that before you take the column out of this matrix. Okay, this matrix has a name to it. Once it, some books have a name for it. Strong has a name for it. It calls it Q. So I'm going to change the letter from C to Q. If we have an orthogonal matrix, an orthogonal matrix, by the way, means the lengths of the vectors, the column vectors, are 1, and one other thing, the lengths of the vectors are 1. Oh, and the columns are orthogonal to each other. Yeah, yeah. And there are some nice properties about this. Yeah, one of the properties. So we're still in this example. We're going to spend some time on this example because it branches out. By the way, the process we followed was the Gram-Schmidt process to get to this Q, to change this. That was the Gram-Schmidt process. Now let's look into factoring. Oh, but I was interrupting myself. Q has an interesting property, and which I want to show. So this is a property of orthogonal matrix. If you multiply Q with the transpose, let's do that. So 1 over the square root of 5, -2 over the square root of 5, 2 over the square root of 5, and 1 over the square root of 5. Oh, this is symmetric. No, there is a -2 here. So when we do the transpose, so this is Q. The transpose will have the same diagonal as this matrix, but then those two are going to be reversed. So the negative is going to be here, -2 over the square root of 5, and +2 over the square root of 5. And then let's multiply. Oh yeah, so we got 1 over 5 plus 4 over 5. 1 over 5 plus 4 over 5. 2 over 5 minus 2 over 5. -2 over 5. No, +2 over 5 minus 2 over 5. 4 over 5 plus 1 over 5. So it turns out that the transpose of an orthogonal matrix will be the same thing as its inverse. So the transpose is the same as the inverse. You want to take the inverse of that. Remember, there's a long process, the Gauss-Jordan elimination process. Don't bother. If you know that you got an orthogonal matrix, just transpose it, boom, you got your inverse right away. That's super nice. There are other nice properties about orthogonal matrices that make them even more desirable. I was gonna go. Oh, there's a shortcut of this. So let me pause for a moment. Let me press the pause button for a moment here, because I wanted to show you a quick way to obtain this column vector. So this column vector came from the matrix B here. That one, this vector was nice because those two were orthogonal. If all we care is that those two are orthogonal and we don't care about their unit, we can multiply this column by 5. And we can generate a new, so let me put a semicolon here. B prime, nothing to do with derivatives. No, I'm just differentiating this with this matrix. So this one has a different name, B prime. If you multiply this column by 5, we're going to end up with 1, 2, -6, 3. Actually, we can even do more. Now, are those two the same? No, they're not the same. Are those two columns orthogonal? Yes. Multiply them out, -6, +6, add that together. Yeah, they're orthogonal. And that's what we care about this matrix, that the columns are orthogonal. So multiplying this guy by 5 is way easier. Furthermore, I can divide by 3. So we're going to create a new matrix, B double prime, 1, 2, -2, 1. And that's way easier. And if you do the normalization means making them length of 1, the columns length of 1. If you do the normalization, you're going to end up with exactly the same matrix, but it's way easier to work with whole numbers than with this fraction. So this computation was not too difficult, but it was kind of cumbersome because there's fractions and all this. If you replace the vector with a multiple of the vector, so multiplying by 5 and then multiplying by 1/3 gives us this, we still have orthogonal columns, which is what this matrix had, but then making them into unit vectors is faster, easier, not as painful as doing those computations. So I'm going to be using that trick later. You know, if we got orthogonality multiplied by just a constant, and the orthogonality is going to be preserved, and then doing the unit vectors are going to be easier. But we still have to get into the factoring. It turns out that the original matrix A, okay, so now I was pausing this flow of thought. If you have the original matrix A, we can multiply, no, A can be written as Q times a second matrix. I'm going to use the same notation as Strong. Strong calls it R. Yeah. So the question is, what is this? So we're getting into the factoring. Remember the Gram-Schmidt method, then the factoring. Right now we are here in the factoring. Can we write A, which was our original matrix, 1, 1, 2, 5. Can we write 1, 1, 2, 5 as Q, which is this guy, 1 over the square root of 5, 1 over the square root of 5, -2 over the square root of 5, 2 over the square root of 5, and 1 over the square root of 5 times another matrix, And what is that matrix? And that would factor this into an orthogonal matrix times another matrix. And the question, what is that other matrix? Well, the answer is actually quite easy to obtain, quite straightforward to obtain. I shouldn't say easy, straightforward. There's a difference between straightforward and easy. Moving heavy boxes is straightforward, but it's not easy. So, you know, we don't have to think too much about how to move boxes. Well, sometimes we do, but assuming that everything is straightforward, just move a box from one place to another. That's easy to think, but it's not. No. What is that? It's straightforward. That means that there's not much involved in just moving boxes, but it is hard work nonetheless. Okay, so what we can do is multiply on both sides. So going back to this, if we have A equals QR, and we want to know R is this guy, question mark, what we can do is multiply on the left by the inverse. Those two cancel each other. They're going to give us the identity. The identity is R. So that means that R is simply the inverse of Q times the original matrix that we were given. Mind that the inverse of Q is easy because it is simply easy to figure. We don't have to do the Gauss-Jordan elimination because all you have to do is transpose our original matrix and you have the inverse. So finding R is actually very straightforward. R will be the inverse, which is this one, same thing as the transpose, remember, so semicolon. The inverse of Q is the same thing. In this particular case, that's not the case for every matrix. If you got an orthogonal matrix where the columns are nice, straight units, I mean, unit vectors, so their length is equal to 1, and every one of the columns is orthogonal to any other column, then this is going to happen. R is A is 1, 1, 2, 5, 1, 1, 2, 5, and we're going to multiply with this matrix. You know what? This matrix has square root of 5 as a denominator everywhere, so I'm going to factor that out, 1 over the square root of 5 as a scalar, and we're going to multiply with what is left over, which is 1, 2, negative 2, 1. 1, 2, negative 2, 1. And that scalar may factor out, and we can reintroduce it back after we do this multiplication. It's, in my mind, way easier to multiply matrices with whole numbers or integers than matrices that have fractions in it. So 1 minus 2, negative 1. 2 plus 1 is 3. 2 minus 10, negative 8. 4 plus 5, 9. Let me double check. 1 minus 2, negative 1. 2 plus 1, 3. 2 minus 10, negative 8. 4 plus 5, 9. Good. So A, which was 1, 1, 2, 5. Oh, wait a minute. Wait a minute. I just realized I goofed. I put A and Q inverse. It should be Q inverse and A. Whoa, 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 whoa. I'm gonna say stop. Okay, what we did is A, Q inverse, and that is not necessarily the same as Q inverse A, because remember, so I'm gonna put necessarily the same. Okay, so hang on. Let's do it the right way. It could be the same, but matrices are not commutative. So let's do it again. R, I should put 1 over the square root of 5. And this matrix, 1, 2, negative 2, 1 first, and then A second, 1, 1, 2, 5. So we have 1 over the square root of 5. 1 plus 4 is 5. Okay, right there, it's not the same matrix. Yep, so stop, that's wrong. This was wrong. It's a mistake in my part, but a lesson to viewers: take into account where the matrix goes. So to cancel the Q, to cancel that Q, we have to multiply with Q inverse on the left here, and on the left there. Because if we multiply on the right, the Q's will not cancel. Whoa, whoa, whoa. Okay, so 1 plus 4, 5, 1 plus 10, 11, 2 plus 2, 4, 2 plus 5, 7. Try again. 1 and 4, 5, 1 and 10, 11, negative 2. Whoa, negative 2, maybe I was doing this and I didn't see the negative. Negative 2 plus 2 is 0. Good thing I checked. Negative 2 plus 2 is 0. Negative 2 plus 5 is 3. Okay. And then we can put this inside if we wanted to. Shall we? So those two simplify to square root of 5, but then 11 over the square root of 5 remains. 0 is 0, 3 over the square root of 5. So factoring. So what we were doing is this. We were writing A as QR, which is factor the A into two matrices, one of which is on the left orthogonal. So A, remember, is 1, 1, 2, 5, and that should equal to Q. Q is 1 over the square root of 5, negative 2 over the square root of 5, 2 over the square root of 5, 1 over the square root of 5, times R, and we just figured that R is, from this page, square root of 5, 11 over the square root of 5, 0, 3 over the square root of 5. Yeah. And this is an orthogonal matrix. It's not necessarily very pleasant to see because it has like fractions with roots. So, but that's the name of the game. It is what it is. Okay, let me double check. So 1 over the square root of 5. Oh, so let's multiply. Oh, so those two cancel each other out. We get 1 when we do this. 11 over 5. Okay, minus 6 over 5. That's 5 over 5. Yep, we get a 1. Those two multiplied together gives us 2. Yep. 22 plus 3 over 5, 25 over 5. Yep. So that works. So this is the factoring of original A into an orthogonal matrix and an upper triangular matrix, the other matrix. The important thing is that we have this matrix and now we found the other matrix. So that's another kind of factoring. What is the third thing we need to speak about? Change of coordinates. Okay. So we are still under example 2. I'm just elaborating so much into example 2, and it is very likely then that I'm going to ask you those three things. I'm going to ask you to come up with an orthogonal matrix, factor the original matrix into the orthogonal matrix and another matrix, and change coordinates to the new basis. So this is sort of a new sub-example. So we're still on example 2. We're going to continue with example 2. It is the same example all along, but we're going to add one more piece of information. I like pens with a wide point. The only problem with that is that there's a lot of ink. My hand gets all dirty. I mean, it's not a big deal. I just wash the hands, which we have to do anyway. But it gets a little messy. Yeah, it's the price to pay. So let's say I give you, okay, so this is not a new problem. It is still based on the same problem, but I need to add more information. Okay. Let's say there's a point with coordinates using those columns. So let's say, yeah. So point E, I'm just going to call it E, A, B, C, D, E, has coordinates. And I'm just going to make up a number, 5, 6. Rather 6, 7, because 5 shows up a lot here. So 5, 6, 7, using the basis, basis 1, 2, and 1, 5. So this is one way to express this. Another way to express that is E is equal to 6 of those, 6, 1, 2, plus 7 of those. That's the same thing. So it is a point. And you can actually figure the actual coordinates of E. But what is important is that E is made up with 6 of this and 7 of those. Now we want to change the coordinates to that basis. Okay, so the question is, what are the coordinates of E under the basis? And since we already have the basis here, it would be 1 over the square root of 5, 1 over the square root of 5, 2 over the square root of 5, and negative 2 over the square root of 5, and 1 over the square root of 5. Okay, question mark. So what are the coordinates? So 6, 7, and remember, coordinates of a point is a relative concept. This point has coordinates 2, 3 under our standard from a long time ago Cartesian coordinate system. Remember, the Cartesian coordinate system is reasonably new in the history of humanity. It was the mathematician Descartes, I believe, who's made that popular, and that was in Europe sometime. But before that, we have the Greeks 2,000 years ago, but they didn't have a coordinate system. They just have the geometry without the algebra involved in it. So this is a recent thing. in the history of humanity. And 2, 3, at least as far as I know. Um, but so these are the coordinates using E1 and E2, but the very same point has different coordinates using a different set of vectors. A and E1, those are the coordinates. Those are the coordinates under those two vectors. And those are the coordinates using those two vectors. So whatever vectors we use will have different coordinates. So what are the coordinates under those two vectors? Yeah, yeah. Now, we can rewrite this as, let's make the matrix 1, 2, 1, 5, 1, 2, 1, 5, multiplied with 6, 7, the column vector 6, 7. Okay, so let's write this down. So E is equal to the matrix A times 6, 7. Okay, and we want it to be Q instead, and X, Y. Yeah, we want it to be a linear combination of the columns of Q. Remember, that product is 6 of the first column of A, 7 of the second column of A. And we wanted it to be a number of the first column of Q plus another number of the second column of Q. So those correspond to the coordinates of the same point with using the columns of Q instead. So this is really the equation we want to solve for X, Y. Okay. So how do we go about that? It's actually very, very straightforward. So focus on this equation. We want to solve for xy. How do we solve for xy? Divide by q. Well, we cannot divide by q as easily as with regular real numbers. We got to multiply by the inverse of q on the left. So xy is a q inverse on the left, keep the 6, 7 on the right, and that's how we get xy. QA, did we do QA earlier? No, the inverse of Q rather, A. Well, that was R, wasn't it? If we multiply Q on the left, QA equals R. Oh, that is cool because R is gonna change the, boy, that is so cool. So this is the same thing as R times 6, 7, and that's gonna give us the new coordinates. I think that is the coolest thing ever. Boy, I don't know if you can trust the person who says that the coolest thing ever is something this deep in math, but anyway, so what is that equal to? R, there's no point on recomputing R since we already did, square root of 5, and we verified that R is the correct one. So I'm just copying this R matrix. And we are simply going to multiply by 6, 7. So we're going to obtain the answer very, very quickly. 6 of those, 6 root 5, man, plus 77 over root 5, multiplying those two. And then 6 times 0 plus 21 over root 5. Oops, I don't know why I put 25. 21. We want to combine those two, so we want to multiply by square root of 5 over square root of 5. Yeah, so that's going to be 6 times 5 over the square root of 5. So that's 30. So this is really 30 over root 5 plus 77 over root 5. And then the other one is going to be good as is. So 107 over root 5 and 21 over root 5. Okay. So the answer to the question, because the question was, if, let's go back to the question. The question was, if we have those coordinates 6 and 7 for the columns 1, 2, and 1, 5, and we're going to change to those columns, what are the new coordinates? Well, the new coordinates are going to be, so the new coordinates, and oftentimes we write the coordinates horizontally instead of vertical. How did I do it when I was introducing this idea? Oh, horizontally. But the new coordinates are going to be 107 over the square root of 5 and 21 over the square root of 5. So those are the new coordinates of E. The new coordinates of E is this, are yeah, those two. Yeah. Oh, what I was gonna say is, so why are the coordinates so weird? Well, because the columns that we are using, these columns, are kind of weird to start with. Not too bad though, but they're not just nice whole numbers, but they tell us more information than, so this number, whatever it is, we know it's going to be that many units going in one direction, and this is going to be make a turn 90 degrees, and that's going to be that many units in the other direction of the column vectors. So that gives us, it doesn't look very nice, very pleasant, but it does give us meaningful information about the location of E using the column vectors of the orthogonal matrix, which are those two. Okay, this video is getting long, but and there is one other example I wanted to show you. I'm not going to do the whole example, but I do want to show you one part that is critical for that example. You are going to finish the example. So let's do example 3. And again, I'm not going to go through the whole thing. There's just one part that is critical that I want to go through though. Okay, so pretend A is 1, let me read the columns, 1, 2, 3, 0, 3, 5, 2, 3, 16. And we want to do the same thing. We want to go through the Schmidt method. What is the method going to do? It is going to change, well, not the first column. The first column stays the same. The second column is going to be changed, so those two are orthogonal. And then the third column is going to change, so those 3 are orthogonal. Then we're going to make them unit vectors, each one of those individually, each column, and that's going to create Q, which is our orthogonal matrix. I'm not going to go through the whole thing. What I do want to show you is, because we did go through the process of taking this guy and making it orthogonal to that. We're going to repeat that. But we didn't go through how to change that and make it orthogonal to those two. And that's the one thing we want to do. Okay. So I'm going to focus on that. I'm not going to do the whole thing. Let me start with okay, so pretend you got this vector. Let's label this vector as v1, v1, v2, this column vector v3, v1, v2, and v3. So v1 is, I'm going to draw it horizontally, v1. And then v2 is going to be there. They're not orthogonal because they're not a 90-degree angle, because if you multiply and add the products together, you don't get zero. The dot product of those two is not zero. In fact, it is going to be 0 plus 6 plus 15. 0 plus 6 plus 15 is 21. So the dot product between v1 and v2 is 21, which means we don't have 90 degrees. The way to get 90 degrees is if the dot product is exactly 0. But we don't have that. So how do we go about finding a, a substitute for this vector that is perpendicular to v1? So we want this vector, which means we want to find p. I'm going to label it as p2 only because it comes from v2. So we want to find p2. p2 is going to be, let's see, the product of v1, the dot product between v1 dotted v2, divide by v1 dot product with itself. And then we're going to multiply by the vector v1. That's a standard formula for the projection. Many books use instead of the dot product, they use the transpose of v1 as a matrix multiplied with v2. I have a little bit of a problem with that, with using the transpose. There is not a lot of harm done with using the transpose, and easily that extends to matrices. Personally, I have a problem with that, so I'm going to stick with the dot product. Yeah, I don't want to elaborate right now why, but let's just say I do have a little bit of a problem with that. Anyway, so 1, 0, 2, 3, 6, 15, 21. So this dot product is going to be 21 over, and then the dot product of v1 with itself, so multiply this with itself is 1, 2 with itself, 4, 3 with itself, 9. So 1 and 4 is 5, and 9 is 14. And then we're going to multiply with v1, which is 1, 2, 3. 1, 2, 3. See, that's one of the problems. Here we have a scalar divided in scalars is going to give us a nice scalar, which we can simplify. If we did transposes, we're going to end up with matrices. Matrices are technically not the same as scalars. I thought back and forth for a little while in the last couple of days, in the last week, and I arrived to the conclusion that dot products are not the same thing as matrix products. Formally, they're not. And I can elaborate on that, on why of that in a moment, but let me focus on finishing this up. So this is going to be the same thing. Simplify 3 over 2, 1, 2, 3. And remember, this means you can actually multiply each one of those entries by 3 over 2, which is 1.5, which tells us that the projection is the length of this and half of it more. It's a nice, it's a very, very nice actually number, 1.5 past this. That's the projection. Now, we're not going to replace this vector with that vector. That doesn't make sense because they're both on the same direction, and we want to have 90-degree angle among them. So we're going to create a second vector, which we can call, I'm going to use v2 prime. Has nothing to do with derivatives. It's just prime to differentiate it from v2, which is going to be v2 minus p2. Oh, so v2 is going to be 0.35 minus, well, I'm going to multiply with the 3 halves minus 3 halves. Oh, 3, 2 minus, oh, no, no, 9 halves. So we end up with negative 3 halves. Well, that's going to be 0. And that's 10 halves minus 9 halves, 1 half. Okay. Now, in the process of Gram-Schmidt, we are leaving the first column as is. The second column is going to be replaced with something that is orthogonal with the first column. That's the Gram-Schmidt method. Move on to, we're going to wipe this off, but we're going to use the same plane. Those two vectors are on the same plane. This vector is on the same plane as this vector and this vector. So it's not just arbitrarily coming up with an orthogonal. It is an orthogonal, because there's many orthogonal vectors that we could have picked, but this one lives in the same plane as those two. Those two are linked by being on the same plane as those two. But the length of the vector is irrelevant. What we want is this vector. We want to replace, we want to wipe this off with a new vector that is orthogonal to this one. But at this point of the game, we don't care about its length. I see fractions. If we multiply this vector by 2, the fractions disappear, and we end up with negative 3, 0, and 1. So we're going to multiply v2 prime, this new vector, by 2. Excuse me. And so now we have to obtain negative 3, 0, 1. And that seems arbitrary, capricious. So, hey, I'm just going to multiply by 2. But let's understand why it is okay to be that way. So I'm going to come up with a new matrix. We're going to label it as B. The first column is going to remain as 1, 2, 3, 1, 2, 3. The second column, we're going to replace it with negative 3, 0, 1. It's important to realize that this column is a linear combination of those two. That's what I was trying to tell you when I said on the same plane. It is, this column is not just arbitrary. It is a linear combination of those two. 2, 3, 16. And what we gained by having that, replacing this matrix with this matrix, is that those two now are orthogonal. So this is an improvement. Remember, we are trying to improve a matrix. This matrix, it's not, I mean, it generates the columns nicely. The columns generate a space just fine, you know. But we want the generators, the columns, to be more special, to have a characteristic that makes them nicer. And those two vectors are already beginning to fulfill what we want. We want those two to be 90 degrees in between the two. So we want to be able to take corners, 90-degree corners, as opposed to some kind of weird angle corners. Yeah. Having said that, and I'm not saying that square is always best, you know, as far as urban development. If you are a pedestrian in a city, I have found over the years that actually you don't necessarily want all your streets to be square. Square is easy in the sense of, oh, I know where I'm going. You know, you can just go in pretty much 2 directions. Well, 4 directions. Diagonals complicate that. However, if you're a pedestrian, what I have learned over the years is that if you walk a lot in a city, actually diagonals are nice, because then you don't have to go straight one way, make a corner. You can kind of cut through in the diagonal if you have enough diagonal streets. And so that shortens your walk if you're going from place A to place B by walking. That's just a side note. But now let's replace this guy. By the way, the length of this vector is not 1. The length of this vector is not 1, but that's easy to fix. We will fix that later. Right now, let's move on to replacing this vector with a vector that is a linear combination of those 3, and yet it is orthogonal to that and that. Okay, so let's replace it. Okay, so those two generate a plane. So let's label this as V1, V2 double prime, and then this is V3. Okay, so those two generate a plane. So there is V1 somewhere, V2 double prime, because remember we went through 2 transformations to get to V2 double prime. So this is a replacement of the original V2. And then V3 is somewhere here. Actually, it's way farther out, but so there's V3. Now, we have that those two are at a 90, my picture is not, it should have been a better picture. Those two are at a 90-degree angle. This vector was designed, engineered, so that it was 90 degrees relative to this one. That's what this vector has. It's 90 degrees with respect to those two. So my picture is not the best perspective. Now we want to generate a third vector that is 90 degrees with respect to those two. So what we do is we find the projection. Now the projection is not necessarily going to be on this one or on this one. It's going to be on the plane of those two. I'm going to label that as P3. So we want to find P3, and then we're going to subtract V3 minus P3 to get this vector. And the beauty of this vector is that it is going to be 90 degrees with V1 and 90 degrees with V2. Some of you are going to say, why don't you just take the cross product? Point well taken, except if we had a 4x4 matrix or a 2x2 matrix, the dot product is not, well, in a 2x2 case, it doesn't work as good, but in a 4x4, the cross product loses its meaning. It's not as easy anymore. Projections will always give you orthogonal vectors after we subtract from the projection from the vector that is not in the space. But cross products work only exclusively if we are in R3. But if we are in R4 or some other space, the projection is the way to go. So that's why we are focusing on the projection and not so much on the cross product. So that's why we are not doing the cross product. That's a well-taken point, though, because it will work. The cross product between those two will give us our desired perpendicular vector. And there's another thing. We want to make sure that that vector is a linear combination of those 3, and the cross product doesn't necessarily do that. Yeah, so it's the projection is really the way to go. So P3 is going to be, okay, V3 times V1 dotted with V3 over V1 dotted with V1 times V1. So it's got to be a linear combination of this. And it's got to be a linear combination of this guy. So we're going to have V2 double prime, this vector, dotted with V3 over V2 double prime dotted with V2 double prime, V2 double prime. This is what is new. There was no such projection computation when we were dealing with, we just had this part, remember, when we were dealing with example 2. This is example 3. So this part was not there. Rather, this part was not there, just this kind of part. So now we're going to add a second one. If we had 4 columns, and we were going on for replacing the 4th column, then we would add one more such term. And notice that those are the same, v3, which is this vector that we're projecting. And those are the vectors that we are projecting onto. Not, when I say that, I mean the space that they generate. But this is the formula to find P3. Okay, I should be able to squeeze this here for now, at least the scalars. So V1, V3, the dot product is 2. So 1 times 2 is 2, 2 times 3 is 6, 3 times 16 is 48. So 2 plus 6 plus 48, 56. V1 dotted with V1, 1, 4, 9. So 1 times 1, 2 times 2, 3 times 3, 1 plus 4, 5 plus 9, 14. I think that's simplifiable. V1 plus V3 multiplied with so third column dotted with the second column. This column with this column. Negative 6, 0, 16. Negative 6 plus 0 plus 16, 10. And then we dot those. Negative 3 squared. So negative 3 times negative 3 is 9. 1 times 1 is 1. 0 times 0 is 0. So 9 plus 0 plus 1 is 10. Oh, what a happy coincidence. V2 double prime. So I'm going to continue on the next page. The third projection will be, let's simplify this. This is 8 times, so 14 times 2 is 28 times 2 is 56. So this is simplifiable by, this is just 4 times V1 plus 1 times V2 double prime. So remember, V1 is 1, 2, 3. 1 times V2 double prime is negative 3, 0, 1. And that's going to be 4, 8, 3, 4, 8, no, 12. Minus 3 plus 0 plus 1. 1, 8, 13. Okay, this is not the replacement for the third column. We have to take the third column and subtract the projection. So V3 prime will be 2, 3, 16, and we're going to take away 1, 8, 13, the vector we just found, and that's going to be 1, opposite of 5, 3. So now we're going to have a new matrix, C. 1, 2, 3, negative 3, 1, 1, negative 5, positive 3. Now, before I move on, we have to make sure that all the vectors are orthogonal. So we have completed pretty much the Schmidt, the Gram-Schmidt process, but I'm going to make sure that everything is orthogonal. Let's double check. We did check this before, but let's double check. So this times that is negative 3, 0, and 3. That adds up to 0. Good. But we knew that. This with this, 1 minus 10 plus 9, 0. We're good. Now this with this, negative 3, 0, positive 3, yes. So this matrix has columns that are orthogonal among themselves. This column with this column, orthogonal. This column with this column, orthogonal. This column with this column, orthogonal. All the possible ways to pick two columns, they're going to be orthogonal for sure. That's a quality of this matrix. It's a desirable quality of this matrix. We want orthogonality among the columns. It's not perfect yet. Perfect in the eyes of having a good basis is that in addition to, so now the vectors are orthogonal, but now we want them to be unit. But that's easy. I'm going to let you finish that up. Find the length of this vector and divide each one of those by that length. Find the length of this vector and divide each one of those by the length of that vector. Find the length of this vector and divide by each one of those by the length of that vector. I want to finish the video now, but I have not completed everything we have done as we did in the previous example. This is example 3. In the previous example, we found Q. So let me write down the next things to do. Okay, so find Q, which is the orthogonal matrix. C is almost there. That's not orthogonal. By orthogonal, we mean the columns have to be orthogonal among themselves. In addition to that, each one of the vectors has to be a unit vector. That's what I just told you have to do. Once you divide by this vector, this column vector by its length, this column vector by its length, this column vector by its own length, then you're going to end up with Q. So you're going to find Q. That should take you a couple minutes. Then factor the original A into Q times R. So we have A, that's the original matrix. In example 3, there is A, the 1, 0, 2, well, 1, 2, 3, 0, 3, 5, 2, 3, 16. But now we want to factor it. By now you wouldn't have Q, and then you have to find R so that you have this factory. Oh, and there is one more thing. We want to change what is it called? We want to change coordinates. So change coordinates. Okay. So remember in example 2, we had 6 and 7. I'm going to have 6, 7, 8 using the columns of A. So remember? So let's say E is equal to that. 6, 7, 8 using the columns of A. What are the corresponding coordinates, blank, 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 using the columns of Q? So we want to find the coordinates. So there's 3 more things to do. Find Q, factor A into Q, and then find the coordinates 6, 7, 8 from A into Q. Please finish that up on your own. Yep. And yeah, finish that up on your own. And we're going to stop the video here. This was a long video, but I think it is, we have everything that we need to have in this video.